Okay, so in the last video we talked about what momentum is, and so remember momentum is defined as the product of an object's mass and its velocity. Okay, now I also want to remind you that momentum is a vector, which basically means that everything we've talked about as far as vectors are concerned so far this year applies to momentum. And so momentum being a vector also has vector components. I also want to point out that because momentum is a vector and has vector components, that direction matters, and you want to make sure that you're paying very close attention to the signs when you're doing calculations with momentum. Okay, so let's just do a simple example with momentum as a vector. Okay, so example 3 says a hockey puck with mass 2 kilograms slides on the ice at 5 meters per second at an angle of 30 degrees north of east. What are the x and y components of the puck's momentum? Okay, so this is a relatively straightforward calculation. So just to remind you, momentum is mass times velocity. Now there's really two ways to approach this. Okay, so we have a vector. Okay, we have the velocity vector. The velocity vector has a magnitude of 5 meters per second and a direction of 30 degrees north of east. Okay, so one way we can do this is we can find the x and y components of the velocity and then use that to find the components of the momentum. Okay, so for example, let's say I draw a simple coordinate system. Okay, so let's say this is east, this is north, and let's say I have my momentum vector 30 degrees north of east, so something like this. Okay, 30 degrees, and the magnitude, velocity vector, and the magnitude is 5 meters per second. Okay, now of course, Vx would be 5 times cosine 30 degrees, and Vy would be 5 times sine 30 degrees. Okay, of course, we've done this types of calculations many, many times before. And so I can find the components of the velocity vector. So I'm just going to get my calculator. All right, so 5 times cosine 30 is about 4.33. And so I can say Vx is about, let's say, 4.3 meters per second. And then sine 30 is a half, and so 5 sine 30 would be 2.5 meters per second. Okay, and so once I have the components of v, I can find px, that is the x component of the momentum, by just doing the mass times vx. And so that would be 2 times 4.3, which is 8.6 kilogram meters per second. And py would be the mass times vy, which would be 2 times 2.5, which is 5 kilogram meters per second. Okay, and so that would be the x and y components of the momentum. Now, the other way that I could have done this problem, which would be equally valid, was I could have just started off by doing, okay, so momentum is mass times velocity. So if I do 2 times 5, that is going to give me the magnitude, the size of the momentum vector, okay, which would be 10 kilogram meters per second. If I then take that 10 kilogram meters per second and I use the 30 degrees to break that into x and y components, I would find the exact same components that I found down here. Okay, neither one of those is any more valid than the other. Okay, it's just kind of like how 3 times 5 is the same as 5 times 3. Okay, it's the exact same thing, just doing it in a different order. Okay, so don't forget that momentum is a vector. All right, pause there if you need to look at that some more. Okay, so now we're going to talk about what's called change in momentum. Now, change in any value, any quantity, is always the final value minus the initial value. And so when we talk about change in momentum, by definition, change in momentum would be the final momentum, P final, minus the initial momentum, P initial. Or if I expand that out, I could write MV final minus MV initial. Okay, that's not some new fancy equation. That's just like the definition of change in anything is always a final value minus the initial value, and then I'm just replacing what momentum is using the equation with momentum. Okay, so when we talk about doing calculations with change in momentum, It's final minus initial momentum, but you have to be very careful with your signs and directions because of the fact that momentum is a vector, the direction of things matters. Okay, I also want to point out that if an object has an x component of momentum and a y component of momentum, sometimes you have to deal with those separately depending on the context of the problem. Okay, but for now, let's just focus on one-dimensional problems with change in momentum. All right, so example 4. All right, so example 4 says a ball with a mass of 5 kilograms bounces off of the ground. As the ball is falling, it has a speed of 5 meters per second right before it hits the ground. After it bounces off of the ground, it is moving at 5 meters per second upwards. Calculate the change in momentum for this object. Okay, so I want you to pause it here and try to do example 4 on your own, calculating the change in momentum for this ball. Okay, so change in momentum is very simply the final momentum minus the initial momentum. And so this should be a very simple calculation as long as you correctly identify everything that's given. Now, of course, we have the mass, which is 5 kilograms, and we have two velocities, an initial velocity and a final velocity. Now, in this case, when we say initial and final, we mean before the bounce and after the bounce. Okay, so as the ball is falling, it's falling with a speed of 5 meters per second. Okay, but speed and velocity are not the same thing. All right, velocity is a vector, and vectors have direction. And so let's use a coordinate system whereby down is taken to be the negative direction, which is a usual coordinate system that we use. Then I would say that VI would be negative 5 meters per second. Okay, the speed is 5 meters per second, but the direction is down. Okay, because it's moving in the negative direction. That's how I've used my coordinate system. After it bounces off the ground, it's moving at 5 meters per second up, which means V final would be positive 5 meters per second. So when I go to calculate the change in momentum, I have 5 times 5 minus 5 times negative 5, and here's where a lot of people go wrong. When you subtract a negative, it becomes a positive, because this is basically 25 minus negative 25, which is 50 kilogram meters per second. Okay, and so that should be the answer to example 4. That is the change in momentum of the ball. Now, another way to think of this concept is by thinking, okay, so initially it has a momentum of negative 25 meters per, or kilogram meters per second, and then afterwards it has a momentum of positive 25 kilogram meters per second. So basically you can think that it changes its motion twice. It's falling, and so it changes its momentum to stop, and then it changes its momentum again to go back up. Okay, and the total change in momentum is 50 kilogram meters per second. Okay, so please make sure that you pay very close attention to the direction when you're doing calculations with momentum and change in momentum. All right, pause there if you need to look at that some more. Okay, so we're going to come back to this idea of change in momentum here in just a second. Okay, first I want to take us back to Newton's first law. All right, so when we learned Newton's first law last semester, we said net force is equal to mass times acceleration, okay, which is technically true. However, this is actually not the way that Isaac Newton himself wrote this law. Okay, he actually wrote it in a different way. And so let's take a look at how he wrote his own law. Now, acceleration by definition is change in velocity over time. Okay, it's the rate at which an object's velocity changes. Now, I want you to see something. M times change in velocity, that should look kind of familiar to you. Okay, because momentum is mass times velocity, and so mass times change in velocity is the same as change in momentum. Okay, and this is actually how Newton wrote his law, was not in terms of acceleration, but actually in terms of change in momentum. And so basically, the first version of Newton's second law said something like, a net force leads to an object changing its momentum. Okay, so if you take all the forces on an object and you add up all those vectors, then that quantity tells you how quickly the momentum of an object is changing. Now, just to show you one more thing, if you multiply both sides by delta t, which is the time over which the momentum is changing, okay, so times delta t, you get an equation that looks like this. You have F net equals, or times delta t is equal to delta p. Okay, so this thing on the right side, we already talked about that before. That's change in momentum, right? MV final minus MV initial. On the left side, when you have a force and you apply it for a certain amount of time and you multiply those two things, we give that a special name. Okay, we actually call that impulse. Okay, and so the symbol for impulse, let me write this. This is impulse. The symbol for impulse is a capital I. Okay, and so usually we write this equation as I equals F times delta T. Now, in this equation, F, of course, is the force that's being applied, and delta T is the time that the force is being applied. Okay, but based off of this derivation that I just did from Newton's second law, what I've shown you is that this thing that we now call impulse, this F delta T, is also equal to change in momentum. Okay, so in other words, I, which is impulse, is equal to the change in momentum of an object. And this thing right here has a special name. This is what's called the impulse momentum theorem. Okay, there's only two things you need to worry about in this unit: the impulse momentum theorem and conservation of momentum. Okay, so this is half the unit right here in this one tiny little equation, the impulse momentum theorem. Okay, that says that the impulse acting on an object is equal to its change in momentum. All right, so pause there, make sure you have that in your notes. Okay, just to do a simple example. Okay, example 5. It says Mr. Walker is pushing his broken down car with a net force of 100 newtons. If he applies this force for 2 minutes, what will the change in momentum of his car be? Okay, because of the impulse momentum theorem, I know that impulse is equal to change in momentum. Now, when this question asks me to find the change in momentum, it's not talking about MV final minus MV initial. Now, how do I know that's not what it's talking about? Well, because they don't give me mass and they don't give me velocity, right? It could be talking about that, but based off of what's given the problem, that's not what it's asking me to find. Here in this context, when they say what is the change in momentum of his car, what they're really asking me is what is the impulse he is applying on his car? Because of the impulse momentum theorem, impulse and change momentum are equal to each other. So really, I'm asked about the impulse. Okay, so impulse is F delta T. You take the force that's being applied and you multiply it by the time that the force is acting. So in this case, the force is 100 newtons. The time that the force is being applied is 2 minutes, but I need that in SI units. And so 2 minutes would be 120 seconds. And so that would be an impulse of 12,000. And the unit for impulse is Newton seconds because force is in newtons, delta T is in seconds. Now, before I move on, I do want to point out something very, very, very important about the impulse equation. It's always important to understand the limitations of what you're dealing with. Okay, so in the last unit when we talked about work, we talked about Fs cosine theta. That equation has a limitation that it only is valid assuming the force is constant. This equation has the same limitation. Okay, so when we do F delta T, this equation is only valid provided that the force is constant. If the force changes, then typically what you need to do is you need to apply calculus to solve those types of problems. Okay, but we're not going to do any calculus in this class, although we will talk about another way of solving those problems without calculus later on. All right, so that is example 5. I think on this slide I talk about impulse. We talked about what are the units of impulse, Newton seconds. I like to think of an impulse as like a kick or a jolt. And so remember, from the equation, impulse is F delta t, assuming the force is constant. Okay, but basically what you're doing is you're applying a force for some amount of time. And this could be pushing a car for 2 minutes, but it could also be something much quicker. Okay, so for example, if you kick a soccer ball, okay, your foot applies a force to the ball for some amount of time. Now, it could be a very small amount of time, but there's still some force acting on the ball for some amount of time. Okay, when you hit a tennis ball or a baseball, the bat is in contact with the baseball for some amount of time. Okay, way less than a second, right? A fraction of a second. Okay, but you can still find the change in momentum on that baseball by multiplying the average force times the time that that force is acting. Okay, um, and really, if you want to give a greater change in momentum, what you want to do, whether you're playing tennis or you're playing baseball or if you're doing boxing, usually what they tell you is to kind of follow through with your swing um, in those activities. And so the idea of following through, let's say when you hit a tennis ball, is if you increase the amount of time that the force is acting, that's going to lead to a bigger impulse, which means a bigger change in momentum, which means that the ball is going to fly off faster. Okay, and so that's why usually in baseball or tennis or other sports, they tell you to follow through with your swing. Same thing with like golf and stuff. Okay, it's about giving a bigger impulse to the object. All right, so example 5.5 we'll get to in just a second. The impulse momentum theorem we've already talked about. Do make sure you add this into your notes. Like I said, there's only two big things in this unit, two subtopics in this unit, the impulse momentum theorem and conservation of momentum. And so this unit is super, super short. We're basically halfway done with this unit just from this one theorem. Okay, so we're just going to do a few more examples and then we'll be done with basically half of the unit. All right, so example 5.5. It says Mr. Walker is pushing his broken down car from rest. It has a mass of 1,200 kilograms with a net force of 100 newtons. Calculate how long Mr. Walker would have to push the car to accelerate it up to a speed of 15 meters per second. Okay, so I want you to use the impulse momentum theorem and try to do this calculation on your own. Calculate how long Mr. Walker would have to push the car to accelerate it up to a speed of 15 meters per second. All right, so in any problem, you want to start by identifying some givens. Okay, so I'm pushing my car from rest, which means the initial velocity is going to be 0. I have the mass of the car, and I'm given the force. How long is always a question about time, so I'm looking for delta t. And I want to know how long it takes for me to push the car so that it's moving 15 meters per second. Now, this is not really realistic, by the way. 15 meters per second is like 30 something miles per hour. By the time it gets that fast, I'm probably not pushing the car anymore. I've probably fallen down. But anyway, let's say this is V final, and let's just say I'm pushing it in the positive direction. Okay, so if everything is moving in, let's say, the positive direction, there's nothing in the problem where I really have to worry about the vectorness of the problem. All right, so if I am looking for time, that leads me to believe that I want to look at the impulse equation, because that's really the only equation that has time in this unit. Okay, so I'm looking for delta t. I want to know how long is the force acting. Now, I know what the force is, it's 100 newtons, but that doesn't let me solve for delta t because I don't know anything about the impulse. Okay, I don't know, I'm not given the left side of the equation. But because of the impulse momentum theorem, I do know that impulse is equal to change in momentum, right? Impulse is equal to change in momentum. So if I calculate the change in momentum of the car, I can also set that in equal to the impulse. Okay, so the change in momentum of the car would be mv final minus mv initial. Okay, that would be 1200 times 15 minus 1200 times 0, and that would be 18,000 kilogram meters per second. And now that I know the change in momentum because of the impulse momentum theorem, I can take that and I can plug it back in for I over here. Okay, so that's 18,000. I divide both sides by 100, and I get delta t equals, let's see, that would be 180 seconds, 3 minutes. Okay, so that is a relatively straightforward calculation involving the impulse momentum theorem. Pause it there if you need to look at that some more. Okay, now just to take a look at one more example. Example 6 says two drivers, each with a mass of 100 kilograms, traveling at 10 meters per second, run their car into a wall. Driver 1's car has an airbag which deploys, causing him to stop in 0.1 seconds. Driver 2's car does not have an airbag and his body comes to a stop in 0.02 seconds. Okay, first question says calculate the impulse on driver 1 and driver 2. Now, when you see the question, calculate the impulse on driver 1 and driver 2, your first instinct is to use the impulse equation, which makes sense, right? I equals F delta T. The problem is we're not given any information about the forces on driver 1 or driver 2. In fact, the second question asks us which driver experiences a greater force from the collision. So the fact that we're not given force, even though we're given delta t in the problem, leads to me to believe when it says calculate the impulse, it's probably asking me to find the change in momentum. Okay, remember the idea is that those two things are one and the same because of the impulse momentum theorem. Okay, so I'm going to start by calculating the change in momentum for driver 1 and driver 2. I know that they're both traveling at 10 meters per second, and then they run into a wall. Now, if they run into a wall, they're going to stop, which means V final is going to be 0, which means that the 10 meters per second is going to be VI. Okay, let's say they're initially moving in the positive direction. And so I can find the change in momentum for the drivers. That's going to be, let's see, 100 times 0 minus 100 times 10, which is negative 1,000 kilogram meters per second. Now, wait a second. Wait, for which driver did I do this calculation? Okay, well, it turns out it doesn't matter. All right, because both drivers have the same mass, they both have the same initial velocity, they both have the same final velocity because they both stop. And so even though one has an airbag and one does not, they both have the same impulse because they both have the same change in momentum. So driver 1 has a change in momentum of negative 1,000 kilogram meters per second, and driver 2 also has a change in momentum, an impulse of negative 1,000 kilogram meters per second. Okay, now does that mean they have the same outcome? No, right? Obviously, the one the one who doesn't have an airbag is going to be in trouble. Okay, but they both have the same impulse, and that's just because of the circumstances of the situation. Right? In this situation, because they have the same initial values and final values, they have the same change in momentum. Now, the second question says, which driver experiences a greater force from the collision? Now, they might have the same impulse, right? But that doesn't mean they have the same outcome. And so remember, impulse is F delta T. So let's assume here that the force is constant so we can use this equation. Driver 1 has an airbag, and so driver 1 stops in 0.1 seconds. That means that the force that's acting on driver 1's face lasts for 0.1 seconds. So that's my delta T for driver 1. So I can calculate the force on driver 1 because I know the impulse is negative 1,000. And so if I plug in 0.1 for delta T, I get negative 10,000 newtons. Okay, so that is the force acting on driver 1, which is quite a lot. Okay, but it could be worse. What about driver 2? All right, so this is, let me label this. This is for driver 1. Okay, so what about for driver 2? So driver 2, the calculation would be the exact same, right? The impulse would be the exact same, but now delta t is going to be 0.02 seconds. In other words, because driver 2's car does not have an airbag, it takes him less time to stop. All right, less time to stop is bad in this situation because that means when we go to divide to find the force, we have negative 1,000 divided by 0.02, we actually get negative 50,000 newtons on driver 2. Okay, and so we see a very real-life application of the impulse momentum theorem here. Okay, why does an airbag protect you? Okay, what exactly does an airbag do to protect you? From a physics standpoint, what the airbag does is it increases the amount of time that it takes your body to stop. Okay, the impulse is going to be the same one way or the other, right? Because your final velocity is going to be zero one way or the other. Your initial velocity has to do with how fast you're moving before the collision. Okay, so the only thing that the airbag can do is change how long it takes you to stop. Okay, the longer it takes you to stop in the situation, the less force is going to act on you. Okay, and so that's how airbags save lives, by making it take longer for you to stop. All right, so pause it there if you need to look at that some more. All right. Okay, and just to show you one more thing really quickly, okay, I want you to take a look at this clip, and I want you to answer the question, why does the egg not break? And this is not like a random question based off of what we literally just talked about in the last example. Why do you think the egg does not break in this video? Okay, so try to answer that. Okay, so exact same concept with the impulse momentum theorem. One way or the other, the final velocity of the egg is going to be 0. Okay, the initial velocity of the egg has to do with how fast you throw it. Okay, if you throw it against a wall, it's more likely to break because the egg is going to stop in a very short amount of time. Less time means more force. But if it hits something soft like a bed sheet, okay, that extends out the time it takes, right? If the impulse is fixed, if you make delta t bigger, the force acting has to be smaller, right? And so the egg doesn't break because the bed sheet makes it take longer to stop, which decreases the force on the egg. All right, so I'm going to go ahead and stop it there. We'll talk a little bit more about this at the beginning of the next video, but that's basically the concept of the impulse momentum theorem. Okay, what we talked about in the last slide with the airbag and all that stuff, that was just one simple application of the impulse momentum theorem. Um, Remember, in that situation, the impulse was only fixed because of the the fact that the final velocity and the initial velocity had nothing to do with the airbag being there or not. Okay, and so that was just like one like special situational application of the impulse momentum theorem. But you should now be able to do most of the problems on your impulse momentum theorem worksheet. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.